Okay. Okay, Aleo Legaris Adrian. Aleo Legaris Justin. Dingy. Here. Francois. Quotes.
Here.
Times. Hodges.
Here.
David. Lee.
Here.
Malmberg is here. Martin.
Here.
Medina is here. Moreno is here. Perush. Simmons. Wheeler.
Here.
White. And Zaragoza. Good. So, we're going to continue our discussion of chapter 5. I just want to mention that based on what we have covered so far, based on, okay, so based on what we have covered so far, you should be able to do all questions up to and including chapter 7. All right, because I think, just to remind myself, I think we did up to this question here, right? This example. Did we cover this example last time? Where we calculated the pressure of oxygen, they gave us the density, temperature. We did this one? You don't see it in your notes? In fact, let me do a quick check of something here. We see here. Okay, so the last class we had was 25th. Let me just check over here because the Wi-Fi is really not cooperating today. Okay, I guess we didn't do this one That's the next topic. Okay, so um, okay. So I think I need to go back to. Okay, so this I think this was the last problem we did. So let's talk about oh, wait a minute. Okay, so let me start from here. All right. So basically, and if you've heard this before, I apologize. I just don't remember where we stopped the last time. So what we're going to look at is how do we use the ideal gas law to determine other things about gases? For example, the molar mass of a gas, right? So you should know from before that there's a relationship between the molar mass of a gas and the actual mass in grams, and that would be the moles, right? So the molar mass, by definition, is the mass in grams per mole of a substance. So what we're doing here is using uppercase M to represent the molar mass and lowercase m to represent the mass in grams, all right? So if we keep those two terms in mind, then the relationship between uppercase M, lowercase m, and the moles will be given by this equation right here. And we can rearrange this equation to get the moles being equal to the mass in grams divided by the molar mass. Now, based on the ideal gas equation, we can also have an expression for the moles being equal to PV over RT. So therefore, because n is equal to this and n is equal to this, then these two expressions will be equal to each other, right? So therefore, when we put that in place, where we get this, we can rearrange it to get an equation for the molar mass of a gas, right? So as you can see here, the molar mass of a gas, based on what we have just done, would be equal to the mass in grams times the molar gas constant times the temperature divided by the pressure times the volume, all right? And basically, once you know those terms on the right side of the equation, you put them in, then that will give you the molar mass of the gas, right? So here is an example of a question where this equation is applicable. So the question gives you the mass in grams of the gas, it gives you the volume, it gives you the pressure, and it gives you the temperature in Kelvin. And the question is asking for the molecular mass, right? So as we said before, the molar mass equation is given right here, right? And all we have to do is put the numbers in, right? So for the mass in grams, the lowercase m, that would be 0.550 grams multiplied by R, which is a constant. It's always going to be 0.0821 liters atmospheres over mole Kelvin, multiplied by the temperature, which is 289 Kelvin. And then we divide all of that by the pressure, which is 0.968 atmospheres, times the volume, which is 0.200 liters. And then you do your number crunching, and you end up with 67.4 grams per mole. And that would be the molar mass, all right? But remember, the question is asking for the molecular mass. And if you should recall, especially if you have had me before in intro, or even in this course, I've said, and I've emphasized the fact that the molar mass and the molecular mass are numerically the same. So basically, once you get the molar mass, all you have to do to get the molecular mass is change the units from grams per mole to AMU. So that's why I added this line right here. The molecular mass is equal to 67.4 AMU because the molar mass is 67.4 grams per mole. All right. And that's basically how that one is done. All right. Any questions about this? Questions? Questions? Okay, so if there are no questions, let me move on to the next slide. And in this case here, they're asking for the same thing. Now, the difference is that they're giving you some values in some other units, different from the units that we saw earlier, previous slide, right? So they're asking for the molecular mass of a liquid that when vaporized at 100 degrees Celsius and 755 torr, yields 185 mils of a vapor that has a mass of 0.523 grams, right? So you're using the same formula. Now, the mass units is the same, so we're going to put 0.523 grams here, multiplied by R, which is again 0.0821 liters atmospheres per mole Kelvin, multiplied by the temperature. Now, they gave you the temperature in Celsius, right? So what you'd have to do is convert that temperature to Kelvin. So how do you convert from Celsius to Kelvin? You add 273. So 273 plus 100 degrees gives you 373 Kelvin, right? Then we divide by the pressure. Now here they gave you the pressure in torr, 755 torr. What we have to do is to convert that pressure from torr units to atmosphere units. So that's the reason why I multiply by this right here, right? So you'll notice you have 1 atmosphere divided by 760 torr. You multiply this by this, and that will give you the corresponding pressure in atmospheres. And then finally, we multiply by the volume, but they gave us the volume in milliliters, right? So we have to convert that to liters. So that's what I was doing right here. 185 mils, we multiply by 1 liter over 1,000 mils, and that converts your volume unit from milliliters to liters. And then you do your number crunching, and according to my calculation, the answer is 87.7 grams per mole, right? So therefore, the molecular mass will be 87.7 AMU, all right? So similar to what we did before, but you have to take into account the units. In this case, the units are not in the units that were given in the previous example. So you have to do the appropriate unit conversion before you do the final computation. Another thing I want to stress too is that you'll notice when I'm setting up all these equations here, and I think I've done so in the previous examples. I think there was one using the ideal gas equation. Again, I'm going to emphasize, make sure that you include your units as a part of the whole setup so that you can see how the units will cancel. So for example, in this particular case, the liter units cancel out here and here, the milliliters cancel out here and here, the Kelvin cancel out here and here, the atmospheres cancel out here and here, the torrs cancel out here and here. So the only unit remaining are the units that are circled right here, the grams and the moles, grams over moles. So therefore, that's why the final units here, when you're doing the calculations, grams over moles, and that's how you get that. So it's very important that you show the units in your setup so that you can see what units will cancel out and what units will remain at the end of canceling out all the other units. Okay, any questions about this particular example? Any questions? Questions? All right, so let's talk about the applications of the ideal gas laws. We looked at one application in terms of determining the molar mass of gases. We can also manipulate the ideal gas law to get an expression for calculating the density of a gas. Now remember, typically the density of gases are expressed in grams per liter, right? That is different from solids and liquids. Typically, when it comes to solids and liquids, we express the densities in grams per milliliter, right? Now, remember this equation that we had before for calculating the molar mass of a gas, right? Now, we can rearrange it such that we have M over V on one side. And of course, you should recognize that M over V is the density, right? So if you rearrange this equation where you get M over V on one side, then you're going to get this expression right here. M over V is equal to M, and I should make a distinction again between uppercase M and lowercase m. So lowercase m over V will be equal to uppercase M times the pressure divided by RT, right? And M over V, of course, as stated here, will be the density. So therefore, we can simplify the equation to get the density is equal to the molar mass, uppercase M, times the pressure divided by R times the temperature, all right? And that's basically how we can get an expression for the molar mass, right? Now, based on this equation, there's some interesting relationships one can identify between the density on one side and some of the terms on the right side. So for example, as stated here, the density of a gas is directly proportional to the molar mass, right? Because you have B here is equal to M times P over RT. So what this is saying is that if the pressure is the same, let's say you're comparing different gases, right? The pressure of the gases will be the same, the temperature will be the same, and of course R would be the same. Then basically, the greater the molar mass of the gas, the greater the pressure of the gas, right? So everything else being the same, if the gas has heavier molecules, then the pressure exerted by, I should say not the pressure, I'm sorry. The density of the gas will be greater if the molar mass is greater, all right? So that's one important relationship that we can identify based on this equation. Another important relationship is the relationship between pressure and density, right? As you can see from this equation here, the greater the pressure of the gas, the greater will be the density of the gas, all right? And then another important relationship is the inverse relationship between density and temperature, right? As you can see from here, because the temperature is down here as the denominator, the greater the temperature of the gas, the smaller or the lower will be the density of the gas, all right? So those are just some relationships you could identify based on this equation. So if I gave you a question, just going to make a question. Let's say I gave you O2 and CO2, right? And I ask you which one has a greater density. If the pressure and temperature and everything else is the same, right? But which one has a greater density, right? Then all I have to do, I don't have to do any fancy calculation. All I have to do is look at the molar masses, right? Oxygen, if you calculate it, has a molar mass of 32.00 grams per mole, and carbon has a molar mass of 44.00, what do I say? 0.02. Okay, what's going on here? Grams per mole. I don't know, this thing is not responding immediately. Okay, anyway, so basically, because carbon dioxide has a greater molar mass, then we can tell that the carbon dioxide gas would have a greater density compared to oxygen, provided that the temperature, provided that the pressure is the same for both gases. So you don't have to do any fancy calculations to make those kind of comparisons if you understand what this equation is telling you, all right? Okay, so here's an example of using that same equation to calculate the density of a gas. They gave you the mass in grams per liter, they gave you the temperature, and they gave you the pressure. So it's all a matter of plugging the numbers in. Density will be equal to M, which is the molar mass. So you have to go to the periodic table and you have to add up the molar masses of all the elements according to the formula. You have carbon, which is 12.01. You have hydrogen, its molar mass is 1.008. You have to multiply that by 4. When you add that together, you're going to get 16.04 grams per mole, right? So that's where we get the molar mass from. Then we multiply by the pressure, which is given as 0.978 atmospheres, divided by R, which is 0.0821 liters atmospheres over mole Kelvin, multiplied by the temperature, which must be in Kelvin. 25 degrees Celsius is what you're given. So you add 273 to convert it to Kelvin. That becomes 298 Kelvin. And then you do the number crunching and you get your answer, which is 0.641 grams per liter. All right, so that's basically how that is done. And let me just say this. I think I told you guys before, but it bears repeating, just in case I haven't told you before. All the gas laws, where temperature is required, that temperature value must be expressed in Kelvin, right? So please remember that. If you're given a temperature in Celsius in a question, and you have some problem involving the ideal gas equation or any one of these equations that we just covered, make sure that the temperature is in Kelvin. So if you're given a temperature in Celsius, you need to add 273 to it to get the corresponding temperature in Kelvin. Okay, any questions about this one? Any questions? Questions? Any questions out there in Zoom? Okay, here's another example. Now, this question is asking for the pressure of oxygen. It gives you the density, it gives you the temperature, right? So you're going to use this equation here, but you have to rearrange it to get the pressure, right? So rearranging this will give this. The pressure is equal to dRT over M. The density times the molar gas, constant, times the temperature in Kelvin, divided by the molar mass of the gas, right? So we plug the numbers in. They gave you the density, which is 1.50 grams per liter, multiplied by R, which is this, multiplied by the temperature, which again is 298, converting 25 degrees Celsius to Kelvin. And then we divide by the molar mass, which is for O2, 32.00 grams per mole. And then you do your number crunching again. And according to my calculations, I got the answer be equal to 1.15 atmospheres. And that's pretty much how that is done. Right? Any questions about this one? Any questions? No questions? Okay. So now you should be able to do the questions I mentioned before in the in assignment number 5. You should be able to do questions from 1 through 7. Did I say? I think that's what I said, right? So if you have any problems while doing those, please feel free to come and talk to me about that. All right. Okay, so let's talk about gas stoichiometry or gas reaction stoichiometry. So basically what we'll be doing is looking at what we are learning in this chapter in conjunction with what we learned in previous chapters with respect to stoichiometry. So we're going to look at another law governing the behavior of gases in reactions. And this law is the law of combining volumes. And what this law says is that when gases measured at the same temperature and pressure are allowed to react, the volumes of the gases, reactants, and products are in small whole number ratios. All right. Now, what does that mean? That means that if you have a totally gaseous reaction, right? The reactants are gases, the products are gases, right? Then what you'll find is that the mole ratios of the gases will be according to their coefficients in the balance equation. So for example, the reaction between hydrogen, the reaction between hydrogen and oxygen. Oxygen to form water, right? Now, to write down the balance equation for this reaction, this is the balance equation, right? I'm sorry, folks. Apparently the Wi-Fi is kind of lagging a bit, so. Okay, so that's the balance equation, right? So based on the balance equation, we can see clearly that the ratio of hydrogen to oxygen to water in terms of moles would be 2 to 1 to 2. All right? So that is true in terms of the moles. What this law is saying is that if the temperature of these gases and the pressure of these gases are the same, the mole ratios will be the same as the volume ratios, right? So as stated here, at a given temperature and pressure, 2 liters of hydrogen will react with 1 liter of oxygen, right? 2 liters of hydrogen will react with 1 liter of oxygen. That's because 2 moles of hydrogen will react with 1 mole of oxygen, provided, and this is very important, provided that the temperature and the pressure of all the gases are the same. All right? So basically, there's a 2 to 1 volume ratio between the hydrogen and oxygen at the same temperature and pressure, right? I think I have another example here. Oh, the reaction between nitrogen and ammonia. So let me write down that equation here. The reaction between nitrogen and ammonia to form, between nitrogen and hydrogen to form ammonia. That will be N2 plus H2 to give NH3. All right. So to balance this, we're going to need a 3 here and a 2 here, right? So based on this equation, it's a 1:3:2 mole ratio between the nitrogen, hydrogen, and ammonia, right? So the same would be true for the volume ratios, again, if the temperature and pressures are the same. In other words, 1 volume unit of nitrogen will react with 3 volume units of hydrogen to give 2 volume units of ammonia. Now, the example that I have here is that 6.0 liters of hydrogen will react with 2.0 liters of nitrogen to form 4.0 liters of ammonia, right? So the ratio in terms of the volumes would be 6:2:4, which is the same as 3:1:2, which is what we can see here. 3 volume units of hydrogen will react with 1 volume unit of nitrogen to give you 2 volume units of ammonia, right? So again, we see that this law works when it comes to gaseous reactions. And again, this law only works because the temperature and the pressures of all the gases involved are the same, right? Once that is true, then basically the volume ratios will be the same as the mole ratios. Okay, so, and this last line here is basically saying that we don't even need to know what the temperature and pressure conditions are, as long as they're the same for all the gases involved in the reaction. All right, so let me clear this here. And move on to the next slide. So this is a pictorial example of the reaction between hydrogen and oxygen. Okay. And oxygen to form water. Okay, so we need a 2 here. We need a 2 here and a 2 here. All right. So remember now it's a 2:1:2 ratio. And in this particular diagram here, you have 2 moles of hydrogen, 1 mole of oxygen to form 2 moles of water. All right. Now the same will be true for the volume. At a fixed temperature, the volume ratio will be the same, right? So the assumption is that these flasks all have the same volume. So therefore, whatever the volumes of these 2 here are, they're the same. So 2 volume units of hydrogen will react with 1 volume unit of oxygen to form 2 volume units of water, right? And that's because each of the identical flasks contains the same number of molecules, all right? So this is basically what will happen in this particular gas law, right? The volume ratios would be the same as the mole ratios, again, provided that the temperature and pressures are the same for all the gases involved. Okay, so based on what we have just learned, let's see if we can do this particular example. So this question says, how many liters of carbon dioxide are consumed for every 10.0 liters of carbon dioxide? I'm sorry, let me repeat, or let me go back and correct. How many liters of oxygen are consumed for every 10.0 liters of carbon dioxide produced in the combustion of liquid pentane if all the volumes are measured at STP? So, what do you think would be the very first step you would take in order to answer this question? The very first thing you need to do before you do anything else. Exactly, you're going to need a balanced equation. Okay, so based on the information provided, what would be the formula for the reactants? What would be the formula for the reactants? Yes, ma'am.
C5H12.
C5H12, which is a liquid, plus what?
O2.
Plus O2. Okay, and then what would be the products of this reaction? What would be the products of this reaction? Yes, ma'am.
Carbon dioxide.
CO2 gas and H2O gas. All right, and in fact, oxygen is a gas as well. Okay, so far so good. Now the next step would be what? Balance the equation. So how do we go about balancing this equation? Well, come on, this should be easy, folks. I was just teaching this to my intro class. That's before you guys walked in. Well, come on. How would you balance this?
Would be 8 oxygen.
So you're saying 8 oxygens here? Okay,
5 carbon dioxide
5 carbon dioxides
and 6 water.
and 6 H2O, let me see. So 5 carbons, 12 hydrogens, 16 oxygens, 5 times 2, 8, 10 times plus 6. Okay, so yes. So this will be the balance equation right here. Okay. So the next step, now that we have the balance equation, we start working with the 10.0 liters of carbon dioxide. And the question is asking for how many liters of oxygen gas would be produced. So the question now becomes, what do we multiply the 10 liters of carbon dioxide by? And in order for us to get to liters of oxygen, in order for us to figure out what goes here, we look at the volume ratios, which will be the same as the mole ratios, between the oxygen and the carbon dioxide. So as you can see here, there's a 5 coefficient for the carbon dioxide, there's a coefficient of 8 for the oxygen. So the way we would represent that here is that we will put 8 liters of O2 above and 5 liters of CO2 below. All right. So based on this, 10 divided by 5 will give you 2. So that would give you 16.0 liters of O2 that would be consumed, which is what the question is asking. All right. Right. And the reason we can do this is because the question says that all the gases are measured at the same temperature and pressure. Right. That's the only reason we can do that calculation. If the temperature and pressure for all the gases are different, then this particular law would not apply. All right. Okay. Any questions about this particular example? Any questions? Any questions? Okay, moving along. Let me clear this. And move to the next. Okay, so now we're going to look at situations where the pressure and temperatures may not be the same, right? Things are a bit more complicated when you're trying to do stoichiometric calculation for reactions where that's the situation, right? So, so as we said before, that law that we just discussed, the law of combining volume, only applies when all the gases are at the same temperature and pressure. So basically, in order for us to deal with other situations where that is not the case, we have to basically use the same stoichiometric methods that we learned earlier, plus the gas law. All right. So basically, just to remind you of what we learned in chapter 3, stoichiometric calculations basically comes down to what you're looking at here on the screen. You need to establish the mole ratio between two different substances. That, of course, is based on the balance equation, right? And therefore, you're going to multiply this conversion factor by the moles of one substance to get the moles of the other substance, right? Now, let's say, for example, you deal with a gas, right? Let's say A is a gas, right? Then basically we need to use the ideal gas equation to find the mole, right? So PV is equal to nRT. That's the equation you're going to use. You're going to find N, and that would represent the moles of that particular gas, A, right? And then now you use this to get the moles of, let's say D is a gas, to get gas B, right? So you multiply the moles of gas A by this mole ratio to get the moles of gas B. And then depending on what the question is asking for, you need to use the PV is equal to nRT equation to find, let's say, the question is asking for the volume, or the question is asking for the temperature or pressure, depending on the information given and what the question is asking for. So basically, this is how we combine what we learned in chapter 3 earlier in terms of stoichiometry to what we're learning now in this chapter dealing with the ideal gas equation. So I think I have an example lined up here, which illustrates what I just discussed, right? So this question talks about a compound, sodium azide. It says here that it's used in automotive airbag safety systems. I don't think that is used anymore. But basically what happens is that sodium azide, when you hit it or if it's subject to some sort of shock, it spontaneously decomposes and form nitrogen. So what they used to do is that they put this in the airbag, and then if something happens, they have a mechanism which triggers it, and then nitrogen is produced and it inflates the airbag and protects you from any injury. But I don't think they're using that anymore. I think they're using something else. But anyway, so fortunately for us, they gave us the equation for the reaction, which is balanced, right? And the question says, what volume of nitrogen measured at 25 degrees and 0.980 atmospheres is produced by the decomposition of 62.5 grams of sodium azide? So basically what this question is saying is that it gives you 62.5 grams of NaN3, and they're asking for the volume, presumably in liters, of ammonia at 25 degrees Celsius, and P is equal to 0.980 atmospheres. This thing is still lacking. Okay, so how do we solve this problem? What I will do is start off with the 62.5 grams of sodium azide. All right. And the first thing I would do is I would convert this to moles. Right? Now, being the lazy person I am, oh, somebody said something in the chat. Oh, okay. I'm going to use my trusty molar mass calculator to calculate the molar mass of sodium azide. So Okay, so sodium azide, Na, and 3. And 65.01 is the molar mass, so. Um. So I'm gonna multiply by 1 mole over 65. And okay, let's try this. 65.01 grams, right? So this would be for sodium azide, Na, and 3. And N, K, and I guess I can't erase that. Okay, so. Okay, so that's the first step, right? Ignore this right here. So basically, we're converting from grams of sodium azide to moles. Now, the next step is the mole ratio between the sodium azide and the nitrogen, right? So the way we're going to deal with that is we're going to put 3 moles of nitrogen above as the numerator in this conversion factor, and 2 moles of sodium azide below in the denominator, all right? So that this will cancel out with that, all right? So what I will do now is calculate the moles. So let me get my cheap calculator here to find the moles of nitrogen. And that would be 62.5 divided by 65.01 times 3 divided by 2. And according to my calculation, this works out to be equal to 1.44 moles. And please, of course, as usual, check to make sure I'm doing the right thing, because of course I can be wrong. All right, so that's what I got so far in terms of the moles of nitrogen. Now, remember, the question is not asking for the moles of nitrogen. The question is asking for what? The volume of nitrogen, right? So this is where the PV is equal to nRT equation comes in. So basically, you have to rearrange that equation to get an equation for V, and that would be equal to nRT divided by P, all right? And the N would be the number of moles that we just calculated here. So I'm going to put that here, 1.44 moles. And then I'll multiply that by R, which is always 0.0821 liters, atmospheres over mole Kelvin. And then the T is 25 degrees. Again, that must be converted to Kelvin always, right? So 298 Kelvin. And then I'm going to divide all of that by the pressure. What's the pressure? The pressure is 0.980 atmospheres. So that's the setup. Let's do the number crunching. 1.44 times 0.0821 times 298, and then divided by 0.98. And according to my calculation, rounded off to 3 sig figs, I got 35.9 liters. And of course, the answer would be liters because the mole units will cancel out here and here. The Kelvin units cancel out here and here. The atmosphere units cancel out here and here. So the final units remaining would be the liter unit, right? So that would be the answer, 35 0.9 liters. All right? Any questions about this one? Okay. Any questions about this particular example? Any questions? Questions? Okay, let's move along. So all the gas laws, or all the examples that we have looked at, I should say, we were assuming that we're dealing with just one gas and we apply the gas law, whatever the gas laws are, to that one gas. What we're going to talk about is how do we deal with a situation where we have a mixture of gases, right? So there's a law which covers this particular situation. We call this Dalton's law of partial pressure. And basically what this law says is that the total pressure exerted by a mixture of gases would be equal to the sum of the partial pressures exerted by the separate gases, right? So if you have a mixture of gases, such as the air we breathe, right? The air we breathe is a mixture of mainly nitrogen, then oxygen, and then you have carbon dioxide and some other gases. The total pressure of that mixture would be the sum of the pressures of the individual gases in that mixture. And this is based on the idea that each gas will independently exert their own pressure, so that the total pressure will be the sum of the pressures of the gases. Now, mathematically speaking, we can express it this way, right? P total, that's the total pressure, will be equal to the pressure of gas 1, plus the pressure of gas 2, plus the pressure of gas 3, and so on and so forth, all right? Now, each of these gases, of course, will obey the ideal gas equation, right? So basically, we can write down different expressions based on the ideal gas law for each of these gases. So for gas 1, right, P1 will be equal to N1 times RT over V. For gas 2, P2 is equal to N2 RT over V, and so on and so forth, right? Now, let me get out this here, because we can find or derive some other relationships, some other equations, as soon as this comes up. Okay, so so as I was saying before, so P1 is equal, okay, so P1 is equal to N1 RT over B, right? And then P2 will be equal to N2 RT over V. And then P3 would be equal to N3 RT over B. So you'll notice that in each of these expressions, on the right side in each case, the only thing that changes would be the N value, right? N1, N2, N3. The temperature will be the same, and the volume will be the same for all the gases. Why? Because they're in the same container, right? So because they're in the same container, the temperature and volume for all the gases will be the same. Okay, so let's see what happens when we add these together, because remember what Dalton's law says. Dalton's law says that the total pressure will be equal to P1 plus P2 plus P3 and so on to Pn, right? So let me I forgot to mention here that the nth gas molecule, Pn, that would be equal to N RT over V. Similar equation, right? So what I'm going to do is plug each of these terms into this equation right here. So what are we going to get? We're going to get N1 RT over V plus N2 RT over V plus N3 RT over V, and so on until you get to plus N N R T over V. All right? Now, if you look at this carefully, you can see that we can factor out RT over V. Let's do that. When we factor out RT over V, then what you'll be left with is N1 plus N2 plus N3 all the way to NN, right? Now, this part here, we can simply call that NT, the total moles, right? The sum of the moles of all the gases in the mixture. So if we call that, or if we designate that NT, then we can simplify this to say that P total is equal to N total times R times the temperature divided by the volume, right? So basically what we're saying here is that if we know the total moles of all the gases in the mixture, it doesn't matter if the gases are the same or different, basically we can find the total pressure by using this equation here. So this equation here is basically a combination of the ideal gas equation along with the Dalton's law of combining volume, all right? So that's basically the result of all the steps that we were looking at just now. Okay, so any questions about this? Any questions? Any questions? Any questions? Okay, so let me see what's up next in the PowerPoint. So we just look at that. Okay, so let's look at this example. This question says you have a 1 liter sample of dry air at 25 degrees Celsius, and it gives you the moles of each of the gases, right? As I said before, most of the air that we breathe is nitrogen, right? 0.0319 moles, and then the next most abundant gas is oxygen, and then we have some other gases which are in smaller amounts. So the question gives you the volume and the moles of each of them, and the question is asking for you to calculate the partial pressure of all the gases in the mixture and the total pressure of the gaseous mixture. So basically, we need to find the pressure of each gas. I'm going to start off with the nitrogen. So the pressure of nitrogen, by the way, the formula for calculating the pressure is the same for all of them. N RT over V, right? So I'm going to use this equation in each case, right? Starting with the nitrogen. So N is given as 0.0319 moles of nitrogen times R, which is 0.08 21 liters atmosphere over whole Kelvin. And then I'm going to multiply by the temperature, which is 25 degrees. Again, you have to convert that to Kelvin. So that would be 298 Kelvin divided by the volume, which is 1.00 liters. All right. So let's see what that gives. 0.0319 times 0.0821 times 298 divided by 1, which is, okay, so according to my calculation, this works out to be equal to 0.78360. So 0.780. And the units here would be in atmospheres. And then we do pretty much the same calculation for the other gases. So in the case of oxygen, everything is going to be the same, except in the number of moles, which would be, in the case of oxygen, 0.00856 moles times 0.0821 liters atmospheres over mole Kelvin times the temperature, which is 298 Kelvin, and then divide by 1 liter. And let's see what that gives. 0.00856 times 0.0821 times 298 divided by 1. So according to my calculation, this works out to be 0.209 atmospheres. And then we do again the same thing, this time for argon. So in the case of argon, that would be, what's the moles? 0.00002 moles times R, which is 0.0821 liters, atmospheres over mole Kelvin times the temperature, which again is 298.
Mr. That the 0.002 is for the CO2.
Thank you very much, sir. Thank you very much for pointing that out. So let me take that out. So for argon is 0.0. For argon, it's 0.0000381. Thank you very much. Okay, divide all of that by 1 liter. 1.00 liters. So let's see what that gives. So 0.000381 times 0.0821 times 298 divided by 1. Okay, so in this case, I got 9.32. Now I have to roll this out to 360. So 9.32 times 10 to the minus 3 atmospheres. And then the last one, I ran out of space. So and what I'm going to do is erase the top one. I'm going to erase it here to do the last one, which is the argon. I'm sorry, which is the carbon dioxide. Okay, so for the carbon dioxide, same calculation, different number of moles. That will be 0.00002 moles times R, which is 0.0821 liters, atmospheres over mole Kelvin times the temperature, which is 298 Kelvin again, and all divided by 1.00 atmospheres. So let's see what that gives. 0.0002 times 0.0821 times 298. And according to my calculation, this is equal to 4.89. No, actually 4, because it's 1 sig fig here. This is 1 sig fig here. So just 4. No, actually 5. I need to roll it up. So this will be 5 times 10 to the minus 3. I got 4.89 times 10 to the minus 3. So you have to roll it out to 5 atmospheres. All right. Okay, so that's it as far as the first part. And then the second part says the total pressure. So basically you have to add up all these values. Now the first one I erased. Can you remind me what that was? The very first pressure I calculated.
0.78.
0.78. Is it 0.780?
Yeah.
Oh, okay. Okay, so I'll add that to the 0.209 plus 5 times 10 to the minus 3 plus 9.32 times 10 to the minus 3. And according to my calculation, when you add these up, P total, do that on here, will be equal to 1.003. And that's how you put it. All right. Okay, any questions about this one? Any questions? Any questions? Nope. Okay, so just to illustrate this whole Dalton's law thing, remember now Dalton's law says that the total pressure of a gaseous mixture is equal to the sum of the partial pressure of the gases in the mixture. So in this pictorial example, we have two gases, helium and hydrogen. The volume and temperature are both the same in each case, right? So in this case, in the case of helium, in the case of hydrogen, the amount of gas present is 0.60 moles, and the pressure exerted by that amount of gas is 2.9 atmospheres. In the case of helium, the amount of gas here is 1.50 moles, and the pressure exerted will be 7.2 atmospheres, right? So this is basically the gases separate, and then when you mix them together, what happens? The total pressure, which is 10.1 of that mixture, would be the sum of the 7.2 and the 2.9 atmosphere, right? And that's because the total moles are the same, right? Well, the total moles would be the sum of the moles of the different gases in the mixture. 0.60 moles of hydrogen plus 1.50 moles of helium. That would be equal to the total moles of the gas. And therefore, if we use the equation I derived earlier, PT is equal to NT times RT divided by V. If you were to put this total pressure, this total volume, and the temperature in Kelvin into this equation, then you're going to get the total pressure being 10.1 atmosphere. All right, so that's basically how that works. Now, I think there's a little question being asked here. What would be the total pressure if 0.90 moles of nitrogen were added to the gas system, right? Well, in that case, all you have to do is add 0.90 moles. Okay, so in this case, you're gonna add 0.90 moles to what was there before, right? So when we add this together, we're gonna get 3.00 mole, right? So basically, you want to use the same equation here. This 3.00 moles will go here in this equation. And then we put the other numbers in, and that will give you the total pressure, and that's how that is done. All right. So you can try that on your own. I won't go through that right now because this thing is slowing me up. All right. So let's see here. Mole fraction, another important term that you need to be aware of when it comes to not only this chapter, but for those of you who have to do Chem 2 in the chapter dealing with colligative properties, you're going to encounter this particular terminology again. So what do we mean by this term mole fraction? It's actually another way of expressing the concentration of one solute in a mixture, in a solution, all right? In this particular case, we're applying it to gases, all right? So let's say you have a mixture of gases, right? And basically the mole fraction would be the number of moles of one particular gas, right? Divided by the sum of the moles of all the gases in the mixture. So that's what this is saying. N1 is the number of moles of one particular gas divided by the sum of the moles of all the gases in the mixture. And please note, because you're dividing in this equation, you're dividing mole by mole. What that means is that the mole fraction will have no units. Because the mole units will cancel out because you're dividing a mole value by a mole value, right? So basically, the mole fraction units would be no units, right? Another thing I should say here is that when it comes to mole fraction values, they would lie from 0 to 1, right? Those are basically the limitations in terms of the numbers that the mole fraction will work out to be, right? 0 would mean that you have nothing present in terms of that particular component. And 1 would mean that basically it's not a mixture, it's only that component, right? So therefore, for mixtures, it's going to lie somewhere within that range, right? Another thing I should mention here is that if you're given the pressure values of the gases in the mixture, then you can use the pressure values to determine the mole fraction based on this equation right here, right? Where the mole fraction is equal to the pressure of that particular gas, right? Divided by the sum of the pressures of all the gases in the mixture, right? And the reason why that is so is because the pressure is directly proportional to the number of moles, provided that the volume and the temperature are the same, right? So basically, we can use this to calculate the mole fraction of a gas in a mixture, even though this is the definition, right? And of course, you can rearrange the equation to get the pressure of one particular gas. If you know the mole fraction, basically you multiply the mole fraction by the total pressure of the gaseous mixture, and that will give you the pressure exerted by that particular gas, all right? Okay, do we have time to do this one? Let's see here. You know what, I'm going to stop here, especially since this Wi-Fi has been slowing me up. So hopefully next class, the Wi-Fi will be behaving itself. Okay, so let me just do a quick peek here and see what questions you can do based on what we have covered in this class. So let me go back to here. Oh. Okay, so based on what we have covered so far, you should be able to do all questions up to okay, up to number 10. All questions up to number 10, you should be able to do them. So you can go ahead and try those, and of course, again, if you have any questions, feel free to contact me concerning those questions. All right? So that's pretty much it for today. So I'll see you guys, but I'm going to see some of you, of course, in the lab. The rest of you, I'll see you guys on Wednesday. On Thursday, sorry.
I would go home. Yeah, come back. President Einstein. Yes, sir. Would you happen to get us for attendance?
Uh. Nope, so let me do that now. And for those of you out there in Zoom,